Okay, so we start again. So the second talk of this afternoon is by Deng from Université de Lorraine. We talk how varieties determine the hyperbolicity.
Okay, so thank Bruno for the presentation. First of all, I want to thank Ludmila for the invitation to this conference. So because of the visa problem, so I cannot come by person. So then I give the talk on Zoom. So actually, so this is a joint work with Bruno Cadorel, who was also the speaker tomorrow, and Cadorel-Yamanoi, and also another joint work with which is a building block of the whole work with Brotbek-Daskalopoulos and the Chicago-Mese. So okay, let's start. So before the talk, I want to make the following convention. So through this talk, so X will always be a smooth quasi-projective variety. So defined over C, and I will write X bar to be a smooth projective compactification of X. So such that the boundary is a simple normal crossing divider. So throughout this talk, I will use this notion, so without too much explanation. And so the whole motivation of this talk is just as Pico asked, so the following nature question. So find a sufficient condition of the fundamental groups of quasi-projective varieties. So such that, so this quasi-projective variety is hyperbolic. So later I will explain the precise notion of the hyperbolic. So to do this, so the starting point, you look at what's the easiest example is one-dimensional cases. So just if so, X is a compact one-dimensional curve such that X is compact. Let's see what can we expect it. So actually, so X will be divided by 3 types. So genus is 0. So in this case, the fundamental group is trivial, so it's P1, and the hyperbolicity property, so it's no. Yeah, when I say a curve is hyperbolic, if it's uniformized by the unit disk. So, and if genus is 1, then obviously, so it's a tori, so the fundamental group is infinite. But the point is that it's abelian. And it's also no hyperbolic because the universal coverage is C. And when the genus is at least 2, so the fundamental group is infinite, but this time it's not abelian. And it's hyperbolic. So therefore, according to this easy example, so we'll see that if we want to find some sufficient condition, we have to exclude the finite cases. So the fundamental group has to be infinite, and also, so it cannot be abelian. So it should be some non-abelian fundamental group should be used to formulate the sufficient condition. Okay, so to do this, first, I have to first say define what's the hyperbolicity of higher quasi-projective varieties. So to do this, let's recall the starting point of hyperbolicity. So actually, so it comes back to the theorem by Emile Picard. So in 1879, so who proved the following 2 results. So the first result is called the little Picard theorem, which says that any holomorphic map from C to P1 minus 3 points must be constant. So this is the little Picard theorem. And later, he proved a stronger version, which is called the big Picard theorem, which says that for any holomorphic map from the puncture unit disk to P1 minus 3 points, so it has no essential similarity at the origin. So in other words, so it will extend to a holomorphic map from the unit disk to P1. So this is the so-called big Picard theorem. And therefore, so in a similar way, so we will define the hyperbolicity for higher dimensional complex manifolds or quasi-projective varieties. So this motivates the following definition. So first, the X is still, as I say at the beginning, quasi-projective smooth varieties. So X is called pseudo-Brody hyperbolic. So if there exists a proper closed, theoretically closed subset, so I should say theoretically closed subset. Z of X. So it should be proper, cannot be the whole of X, such that. So for every holomorphic map from C to X, which is non-constant, so these holomorphic map will be called entire curves, like entire function if X is target C. So for every C, so if it's non-constant, then to factorize through Z, so it has image in this proper theoretically closed subset. So this is a definition of pseudo Brody hyperbolic. Here I added the pseudo because I allowed some special set Z such that it might accept some entire curves. So if X admits no entire curve, then it will be called a Brody hyperbolic without pseudoness. And so you see that, okay, so this is a formulation of little Picard theorem. And actually, so analog, so we can do it for big Picard theorem. So X is called a pseudo, so which I call pseudo Picard hyperbolic. So if also there exists a proper theoretically closed subset Z of X, such that for every holomorphic map from the puncturing unit disk to X with its image is not contained in Z. So its image is not contained in Z, will extend across the region. So namely to extend to a holomorphic map from the unit disk to the projective compactification X bar. So this is called the pseudo Picard hyperbolic. And like the bigger Picard theorem implies the little Picard theorem. So actually a remark is that, so this is stronger, so pseudo Picard hyperbolic. So will imply pseudo Brody hyperbolic. So I think so several years ago, so most people are always studying this notion of hyperbolicity. But recently, because of the work of Buchino, Zimmermann, and Baker, and also Johann Buchino and Baker and Zimmermann, so on the algebraicity of analytic maps, so like the proof of the Griffiths conjecture, etc. So now we are more interested in this notion of hyperbolicity because it will imply some algebraicity of analytic maps. Okay, so I will not talk too much on this main motivation. And in the talk, so I will mainly discuss on Picard hyperbolicity instead of Brody one, since it's stronger. So we can prove it, then it will automatically imply the Brody hyperbolicity. Okay, so this is some analytic version of hyperbolicity. There exists also some algebraic version, so which we are more familiar. So X is of log John type. So it's a notion in birational geometry or algebraic geometry. So if it's a logarithmic codierite dimension, the codierite dimension of the pair. So remember, X bar is a projective compactification, and D is the boundary divisor, which is simple normal crossing. So if this is maximal, so namely, so it's equal to the dimension of X. So this is the definition of log John type of variety. So this is also some positivity in algebraic geometry. However, so there was a stronger notion, which maybe you don't meet the name because I made it. So X is a stronger, which I'm more interested in, is I say strongly of log John type. So strongly log John type. So the name I actually was first used by Jean-Pierre Thomas, but he used it for another notion. So I find this name is more valuable. So then I used here. It's strongly of log John type if so also there exists a proper theoretically closed subset. Which I did Z of X. So such that so for every irreducible closed subvariety of X, which is not contained in Z, positive dimensional, I assume, then V is of log John type. So namely, outside this theoretically closed subset, so every positive dimensional subvariety will be have enough positivity for its log canonical boundary. So here, note that V might be singular, but when say log John type, we just take the smooth models to define this to define to be in log John type. And of course, if it's strongly of log John type, then it's of John type. Okay, so now so we have seen several definitions of hyperbolicity, but now all of the the question of hyperbolicity in those years or in several decades, so around the following tantalizing conjecture by Green-Griffiths-Lang. So actually, which I presented is a stronger form, so which I will say strong Green-Griffiths-Lang conjecture. So long times, so those years, so many problems are related to this conjecture. So though it's still very quite open. The statement is as follows: the X is still as before, is quasi-projective variety, smooth over C. So then the following are equivalent. So first, X is of log-joint type. Log-joint type. So the positivity of the log canonical bundle. And second, so X is strongly of log-joint type. So namely, so we have a stronger positivity in algebraic geometry. And the third is some analytical positivity. X is pseudo hyperbolic. So we expect that those three notions of hyperbolicity are equivalent. So the first two are algebraic ones, and the third is analytic. So it's some essential singularity of puncture disk. And the strong version says that, okay, so we expect that they are equivalent. So for this, the original version, I think, is for projective variety and also say this is general type, then it does not contain thoracic dense entire curve. Here we make a stronger statement. And up to now, so even for surface cases, so this conjecture is still not proved. Okay, so this is the main conjectures which motivates all the studies in those years. So now I want to, after I introduce the notions, so I can introduce the main results which I want to talk and I try to prove today. So the first theorem is a joint work with Benoit Cadorel and Cadorel-Yamanoi. So in last year, we proved that, okay, so X is still quasi-projective. So I will not say X is always quasi-projective smooth variety. So let G be a semi-symbol algebraic group. So algebraic group, linear, complex, defined over C. And then let rho be a representation from the fundamental group. When I say fundamental group, it's topology fundamental group from pi 1 x to GC, where GC is the C points of G, which is heuristic dense. When I say heuristic dense, it means that the image of rho is heuristic closure of image of rho is dense, is heuristic dense in G. And also, I assume that it's big. So this is the important notion, which I will explain its definition later. Then the conclusion is easy. So first, so X is strongly of log-joint type. And the second, so X is pseudo-Picard hyperbolic. So namely, so if we have a linear representation of pi 1 x to some semi-symbol algebraic group, which is heuristic dense and big, then we get the strongest hyperbolicity as we can expect it. And also by the Green-Griffiths-Lang conjecture, we expected that the true statements are equivalent. Although we cannot prove it in general, but at least for this theorem, we can prove them both. Yeah, okay, so this is the main theorem. And I want to say several remarks on this theorem. First, so I want to recall the definition of big. So first, the rho is big, so which a representation is big. So if there exists at most a countable union of proper heuristic closed subvarieties. So here Zi is proper heuristic closed subvariety, such that for every positive dimensional closed subvariety of X, with that V is not contained, in this countable union of closed subvarieties, one has the image, the restriction of rho to this V the fundamental group V will be infinite. So here I take the normalization of this closed positive dimensional subvariety, and I take its image in pi1x. And later, so I take the image of rho via this representation, so it should be infinite. So this is the definition of bigness when I say a representation is big. So we allow some countable union of thoracic closed subvariety such that the varieties contained in them in it is might have finite or trivial image of rho, but outside of those sets, so it should be infinite fundamental group. So this is a definition of big representation. So actually, as we will see later, this definition actually is nature. I will explain later why it's nature. And there was a stronger notion which is called large. So I just recall it, but I will not use it in this talk. So I think Johan Buchenbach will explain it tomorrow. So rho is large. So if we just for every v of x positive dimensional irreducible closed, so the image is infinite. So this is infinite. So we do not allow any such a thoracic counter-union thoracic closed subset. So actually, so the large representation was really related to the Shafarevich morphism, existence of Shafarevich morphism, as explained by Philippe in last lecture. Okay, so this is the definition of bigness. So now I want to recall some history on this result. Actually, when X is compact, so some result has already known. So when X is compact, namely is projective, is a projective variety. So in the statement, it's always quasi-projective. But when X is already projective, so first, so Campana and Clodon, so Philippe, so they are all the speakers of this conference. So they proved that, so with the same assumption, so X is of general type. So namely, Kx is big, so the canonical bundle is big. Actually, so this claim was originally stated by a paper of Zuo, but I think there are some problems in this paper, so I will not talk too much on that. And later, so my collaborator, so Cadorel-Yamanoi, so he proved that so X does not contain thoracic dense entire curve. Contain thoracic dense in high curve. So a bit weaker than pseudo-Brody hyperbolicity, but it's a good direction in that way. And more recently, so as tomorrow we will hear the talk by Johan, so Buchenbach. So more recently, he proved that if pi1, if rho is large, so rho is large, then X is strongly of general type. Moreover, and X is pseudo-Brody hyperbolic. So he will explain this tomorrow. I think that his main point is that he can specify the locus. So where it's non-hyperbolic locus and non-general type locus, he can give a good characterization of those locus. So this is the result of Johan. Okay, so there's also some other results, but I don't have time to explain it. Now the question is that, as I asked at the beginning, we want to find a sufficient condition. I want to know, is this condition good enough? Can we weaken the assumptions? But actually, I want to say the first remark is that the condition is sharp. So you cannot loosen the assumptions are sharp. So there are several conditions. So first, the rho, the thoracic rho, G is semi-symbol. So G is semi-symbol. So you want to see, can we replace it by reductive? But as we see the symbolist case of torus, so if you have a torus, you can always have a representation. Pi1 is always can be have faithful representation to edge of torus, but it's, of course, it's not hyperbolic. So therefore, you cannot replace G symbol by reductive. So this is not possible. So some symbol is essential in the formulation. And second, you want to ask rho is big is essential. So actually, yeah, easy example is that if you take a trivial product of X and P1, so then even previously you have a bigger representation, but after you take such a trivial product, it's not big because on each fibers of X, so it's just a P1, and the representation is trivial when you restrict it to each P1. So therefore, it's not big, and also, of course, it's not hyperbolic. You know that the representation of Pi1x automatically extended to this representation of X times P1, but it's not a big representation. Of course, also it's not a hyperbolic. Therefore, the formulation rho is big is also important to exclude this trivial common example. And also the last one is that pseudo is also essential, because you won't say, can we have a formulation such that it's hyperbolic? Because the bigness, because Pi1x, so is a birational invariant for smooth models, birational invariant. So you can always blow up it. And also the bigness is also, the bigger representation is also birational invariant. So therefore, you should always allow the pseudoness of this the hyperbolicity. So this is some remarks on the main theorem. Okay, so this is the main thing I want to talk, and I will prove using maybe last 20 minutes to prove this main theorem, give a hint of the proof. And I want to say some applications. So as I asked at the beginning, was the hyperbolicity, how Pi1 determines their hyperbolicity. But I want to ask the converse problem. If a variety is not hyperbolic, so then is there some restriction on its fundamental group? So this actually was first studied by Friedrich Campana. So in his project of special varieties and orbifolds. So let me recall it. I think he will explain more details in his talk in Thursday. Campana's special varieties. So when I say special, you see, so we say variety is general type, so if it has enough positivity of canonical bundle. Special is contrary to general type. So Campana called it special type. So let's recall the definition. So as I say, it's always contrary to hyperbolicity. So first, the X is called a hyperbolically special or H special. So if, as I say, it's contrary to hyperbolic, then you can imagine, so if there is a characteristic dense entire curve, so namely FC, the entire curve on X, whose characteristic closure is the whole X. So this is H special. And second, so X is weakly special. Say weakly special. So if for every finite eta cover, so of X and birational modification of this eta cover, so there exists no dominant morphism with connected fibers to some varieties with a log type. So this is dominant with general fibers connected, because this is a morphism between quasi-projective varieties. In general, you cannot have every fiber connected. You only say that you can only expect that general fibers are connected. So when I say dominant morphism with general fibers connected, I will say a fibration in this talk, although I don't think it's a very good notion. So I say it's a fibration. So alternatively, so I say that there exists no fibration from X theta to Y with Y is of joint type. So this is a notion of weakly special quasi-projective varieties. And the last notion is called special. So it's a bit involved to say its notion. I just first quickly recall it. So if for every fibration, every birational model of X, and every fibration, the orbifold base, actually, so it's not the usual base. So it depends on the F. So the orbifold base of F, you have to count the multiplicity of the fibers. So put those multiplicity and you take the minimal and they put the prime divisor in Y. So it's a bit involved to say this, but I mean, it's more than Y. So it's Y and plus some orbifold divisor. This is not log John type. So I think Friedrich will explain the notions in his talk. So then a conjecture by Campana says that so H spatial should be equivalent to spatial, although I think it's very, very difficult. So spatial variety is H spatial and vice versa. And he also proved as the name say. So the name say weakly spatial and spatial. Actually, it's indeed the case. So spatial will imply the weak spatial. But the converse is not true. So this is really strong. Okay, so now I'm able to say a corollary of this of the main theorem, so which is a factorization theorem. So because as I say at the beginning, so you want to say, okay, is it too easy to construct a big representation? So I will tell you that, okay, up to some finite data coverage, we can always, if the representation has infinite image, you can always have a big representation. So theorem is as follows. So X is quasi-projective, still G is some symbol. Okay, and the rho is heuristic dense representation, but here we remove its bigness. So it's just a heuristic dense. So we don't assume any bigness. So in general, you cannot expect the X to be a hyperbolic, but actually, so there exists, so after, so we replacing X by a finite eta cover. So finite eta cover and birational modification, proper birational modification. So there always exists a fibration from X to Y. So it's a fibration and exists a fibration and exists a representation from Y, which is heuristic dense and big. So this tau is heuristic dense and big, such that so the original representation rho is just the pullback of the big representation. So namely, so if we replace X by finite eta cover, so it can factorize through some big representation, which is over Y. And by the theorem, we know that Y is hyperbolic in every sense, so strongly John type and also pseudo-Picard hyperbolic. So in particular, so X is neither weakly hyperbolic so no weakly spatial. Weakly spatial, no H spatial. So it's easy to see this because you see by this the definition of weakly spatial. So it just a direct contrary to the definition of spatial because Y is of John type, and if its X is H spatial, then there's the entire curve on X. Then you push this entire curve with this to Y with this F. Then it's also a heuristic dense entire curve in Y. So it contradicts with the hyperbolicity of Y. So therefore, X is not a weakly spatial nor H spatial. So this is some factorization theorem. And as I say, producing larger representation is a difficult task in general. So we have to really construct the Shafarevich morphisms. But producing big in general is not so difficult. So just based on the previous work by Campana and Kola, so and using some technical results, so we can prove this corollary is a factorization theorem. So I will not explain the precise proof here. Okay, so now I want to say something something result. So as I asked, so what's if X is spatial, then is there some restriction on its fundamental group? So this is the next theorem. So if you assume X is spatial, X is spatial or weak or H spatial. So here weak spatial is not enough. So by the conjecture of Campana, they are equivalent. Then for every linear representation, rho from pi 1x to GLNC, So the image is always virtually nilpotent. So it's virtually nilpotent. So namely, rho pi 1 x has a finite index subgroup which is nilpotent. So this is some restriction on fundamental groups of special varieties, but in the linear case. So this theorem, the multivariate theorem, is a conjecture by Campana. So I have several remarks on this. So first, this theorem is sharp. So it is sharp. So in other words, so we really construct a spatial or H-spatial and H-spatial varieties, quasi-projective variety with a linear and nilpotent fundamental group, but it's not a virtually abelian. Because why you expected more? Because a conjecture by Campana says that his conjecture is really general. He says that a spatial or H-spatial quasi-projective variety or geometric orbifolds in his setting, then its fundamental group should be virtually abelian. So this is his famous abelianity conjecture. Actually, we found examples show that this conjecture in the compact case it should be okay, but in the quasi-projective setting, so we should revise this conjecture as a nilpotency conjecture rather than abelianity conjecture. So this is something, some surprising result when we do this. And okay, as I say, so we have to revise. So we have to revise Campana's conjecture. So namely, we say a spatial or H-spatial quasi-projective variety must have virtually nilpotent fundamental group. So rather than virtually abelian. But in the compact case, this is still true for linear version. So this was proved by Yamanoi. Okay, so this is the main results which I want to talk. Now I want to say something on the main tools. So actually, so the whole during the for the whole proof, there are two fundamental tools. So two technical results, two theorems, which is really technical, some building block for the whole work. So the first one is a joint work with also Yamanoi and Cadorel. So we prove that actually, as I say, the strong Green-Griffiths-Lang conjecture is quite open. But actually, if we have some assumptions, it's true. So still, X is quasi-projective. Okay, and assume so there exists a morphism from X to some A, where A is semi-abelian variety. Such that the dimension of X is equal to the dimension of AX. So namely, X is generically finite onto its image. Then the strong GGL is true, strong Green-Griffiths-Lang conjecture holds. So namely, if X is of log-joint type, then it's equivalent to strongly of log-joint type and the pseudo-Picard hyperbolic. I mean, the three notions which I said is equivalent. So we cannot prove in general the strong Green-Griffiths-Lang conjecture is really difficult. But under this assumption, which is useful in our work, so we can really prove it, and it's actually the main technical result in the proof of our main theorem. So this is and for this proof, it's really difficult. So it's built on some heavy nonlinear theory, and plus some jet differentials, which was initiated by the work of Green-Griffiths. So jet differentials. So I think Lionel Dahondo will explain some techniques on jet differentials, and I will not explain this. Okay, so another theorem is a joint work with Brotbek, so Daskalopoulos, so Daskalopoulos and Chicago-Mese. So it's on the existence of harmonic mappings. So still X is quasi-projective. triangle C. So let G be a certain symbol algebra group linear defined over K, where K is a non-Archimedean local field. So non-Archimedean local field. For instance, so QP, something like that. Find the extension of QP. So if there exists a row equivalent, so if row, let row be a representation of pi 1x to GK. So GK is the K points of this symbol algebra group, which is torusically dense. So then the conclusion is that there exists a row equivalent harmonic mapping. From identity U from the universal covering X theta to NPC space, which is called the Brotbek building. So here it denotes the Brotbek building. It's a Euclidean building. So so exists a row equivalent harmonic mapping satisfying the following property. So first, U is more purely harmonic. And second, so U is locally Lipschitz. And moreover, so this one is really crucial. So it has, so its energy might be infinite. So in general, you cannot expect to have a finite energy. So its energy might be infinite. So this really can happen. But the point is that it has at most logarithmic growth. So the energy has logarithmic growth at around D. So the energy so has at most logarithmic growth. So when around D, so near D, near the boundary divisor. So in other words, so the energy grows really mildly. So some log R is log 1 over R. So it's bounded by below by some log by log 1 over R. R is the distance of choose the boundary. So something like that. So although it might be infinite, but actually, so it's controllable. So this is really a technical result, but we it's just the starting point of the proof. Okay, so in the last 22 minutes, I will explain the proof for theorem, the first theorem, just hyperbolicity if we have a bigger and statistically dense representation. So let me say the proofs of theorem A, the first theorem. And so when we see, so we have to distinguish it with several cases. So first, so if rho, case 1. So I will not prove all the things, so I leave some parts to tomorrow's Benoit-Gador's lecture. So he will do some parts. I will only do a part of the proof. So the point is that if case 1, so if rho is rigid. So when I say rigid, it means namely, so its continuous deformation of rho will be conjugate to rho. So in this case, one can show that rho underlies complex variation of Hodge structure, as Carlos Simpson proved for the compact and some quasi-unipotent monoidal in some cases. So actually, so we found that okay, so rigid is enough to have a complex variation of Hodge structure based on some Mochizuki's correspondence. So I think Benoit will explain tomorrow. So then, so rho, after replace rho by conjugation, so it will define over some number field. So K is a number field. Okay, and then, so we just have two cases, case 1.1. So for some place, non-Archimedean place, so non-Archimedean place of K, so the extended representation. So we have so KV is a non-Archimedean completion with respect to this place. So for this representation is unbounded. exists some V such that this is unbounded, is extended to representation of rho is unbounded. So we already know that rho is heuristic dense. So therefore, when we do the extension, still heuristic dense is still preserved. And moreover, bigness is also preserved. So then we are in a current situation. So if we have G is some symbol, if we have representation heuristic dense, big and unbounded, can we prove something? So actually, for simplicity, I will assume G is almost a symbol. Because some symbol is really, you just reduce it, you can reduce the proof of some symbol to almost a symbol cases because it's a semi-directed product of some almost symbol factors. Okay, so then I want to prove this result in the rest of the talk. And case 1.2, so for every non-median place, so the representation is always bounded. So it's bounded. So in this case, actually, so one can see that it will, rho will induce CVHs with discrete monodromy, and it's big, still big representation. So then it's an Archimedean case and Benoit. So Benoit will explain the proof tomorrow. So how to prove these cases. And the second case is that if rho is non-rigid. So this is a difficult case in general. For the non-rigid case, previously I think a usual technique is that we how to construct some non-Archimedean representation. I think the usual technique is already done by I think it's called Simpson, and ACDU, and Kazakov, and later, so I think also Zuo. So the usual way is that, okay, we find a curve in the character variety. Then we take a point at infinity, we take the completion, evaluation with the point at infinity, and we take the completion. Then we got a non-Archimedean local field such that the representation will be unbounded. But the point is that so the Gromov-Shan series only holds for local field. So therefore, so we cannot directly work on this function field, the non-Archimedean completion of this function field or curve. Usually, so we have to standard ways to do a reduction mode P. But I think the point is that when you do reduction mode P, there are two problems. So bigness will be lost. So the representation when you do reduction mode P, in general, you will lose the bigness of rho. This is the first point. And the second point is that I think it's also crucial. So the heuristic closure of reduction mode P, I'm not sure it's still heuristic closure is some symbol of for the reduction mode P for the new representations coming from the curves on character varieties and reduction mode P. So is the heuristic closure of the new representations is some symbol that I think it's not known. So therefore, we're using an alternative way to prove this actually. So it's a proposition we did. So so assume rho is so non-rigid. So and a big representation heuristic dense. So G is, as I say, G is almost a symbol. Then the point is that we can always construct another representation, so which I denote rho prime to some non-Archimedean local field. So GK, where K is some finite extension of QP for some P prime. So this is so you see this is we always working on the field of characteristic 0. So we don't go to the positive characteristic like the reduction mode P, such that so rho prime is big, and the rho prime is heuristic dense, and last, so rho prime is unbounded. Actually, we from this non-rigid big heuristic dense representation, we construct another representation not in local field, but with the following properties. as we've seen in the case 1.1. In the case 1.1, we also encounter with the thoracic dense big unbounded representation. So this is a proposition which allows us to construct some non-linear representation with some nice properties. And actually, for the proof, it's not very difficult to imagine. Why? Because you see, look at the modular space. The modular space of this, the capital variety of G. So then you look at some K points. So we can show that the boundary representations in this modular space actually is correct compact. But this is, if it's non-rigid, then there's some component which is affine, which is positive dimensional, which is non-compact. But the bounded are pre-compact. Therefore, there must be some points which are unbounded. And thoracic density is also not hard to imagine because thoracic density is some open property. And bigness, so we require some work to show some bigness. So this is a very vague idea, but actually for the proof, it's a bit involved. And if you have interest, just suggest you to look at the paper. Okay, so now I just, in the rest 30 minutes, I want to prove that if we have a representation in the Archimedes cases, which is big, thoracic dense, and unbounded, then X is strongly of log-Jones type and pseudo-Picard hyperbolic. So, okay, I don't have too much time. I will be quicker. So, okay, let's do the proof. Just an Archimedes case. Step one. So as I say, there is a row equivalent by the existence of harmonic mapping, row equivalent harmonic mapping. So from U to the universal covering of X to the building. But so I want to do some a bit analysis. So here for the building, so I will not want to recall its precise definition, but we induce the following data. So I wrote here. So here V is some standard apartments, which is isometric. So here for the building, it's an NPC space, so therefore it is endowed complete metric. So some apartments will be isometric to some Euclidean space, where N is a K rank of G. And so phi is the roots, so actually, so it's some alpha 1 to alpha m, so which is some V star, the dual V, and so W is some affine Weyl group, so which is a semi-direct product of the finite refraction group. So this is a finite group generated by finite reflections, and T is a translation. So then, okay, so then I denote a set of X naught of X, which consists of points such that there exists a neighborhood of X. It will be lifted to some open set in the universal covering, okay, in the universal covering, and it will be mapped to some apartments, which is isometric to Rn, so which is isometric to V here. And I did this composition to be H. So the set of such, so by the theorem of Gromov chain, so this has Hausdorff codimension at least 2 codimension, at least 2. So what I explain now is standard, so it's already known by many people. So we can see it in Philippe's paper and also Buino's paper. So then a standard way you really use those harmonic maps to construct some forms. So you differentiate H, you compose U alpha I with those H. So you take the complex phi differential and take the 1-0 parts. So because it's purely harmonic, what you get here is some holomorphic, a set of holomorphic forms in this set, in this local set. And the crucial point is that because of the apartments are transverse, the apartments can be seen as chats. And actually the transition function are related by some Weyl group. And therefore we can see that this is a canonical choice. This set of holomorphic one forms does not depend on the choice of the lifted here and the choice of apartment here. And therefore, so we get a you can imagine some multi-valued one forms. So multi-valued one forms, so which is really defined over So I denote omega1 to be omega m of, so defined of x naught, which is a set where harmonic maps are regular. So then we are trying to extend those objects, but standard way just to take the differential, you make it to be single value. We just want to take the products. So then you get something here. And we can see that sigma I is symmetric forms of x naught. So x naught and the symmetric forms of omega x naught I. But I think because it's a local elliptic, we can say that sigma I will extend it to x. And because of logarithmic energy, so sigma I, so with some efforts, so it's joint work with Brotbek and Daskalopoulos-Mese. So actually we prove that sigma I is also extended to logarithmic forms here. And in other words, those multivariate forms are algebraic. You can imagine something algebraic defined by something algebraic. So now, now the next step. So step 2, which is standard. You constructed some ramified Galois covering. So it's ramified. So Galois covering, I denote to be expect to x with the Galois group H. So H is the Galois group. So namely, X is the quotient of XSP by H finite group. Such that, so those forms, when you pull back those multivariate forms, it will be single value. And moreover, those single value will be logarithmic forms. Okay, X about log B. So, so when we wrote the papers, we found there are several notions of several construction of spectral covering. So this is called spectral covering. But actually, very recently, I realized that, okay, so there was a standard way by AZU in his paper, and Kazakov, and also Bohino-Klinger has a very nice construction. But recently, I realized that, okay, somehow they are equivalent. So when you do both, so the spectral coverage, what they are done is actually the same. Okay, so I have no time to explain this, but yeah, so it's just the spectral coverage makes some existence of one forms, and moreover, so this is a crucial point. So the ramification locus of the spectral covering is contained in some set. Okay. So I is a pullback of those multivariable forms, as we recall here. It will reflect the information of the harmonic mapping, and it's the common zeros of the eta and eta j. So this is the ramification locus of the spectral covering, and we will use this later. So now the next step. So I have 6 minutes. So let's consider the quasi-algebraic morphism. So because we have forms, we can do algebraic geometry. So using those forms, quasi-algebraic morphism from spectral covering to A. So this is similar as algebraic morphism, but be careful, it's not in general proper. So it's just an algebraic morphism. But then you look at, we want to prove. So actually, a crucial thing is that dimension A xp is equal to the dimension of A xsp. So this is the first factor. And the second factor is that, so this is a log joint type. So the first factor actually, so the proof, we shall use some criterion of fineness of some normal subgroup. So this was originally claimed in Zor's paper, but the proof, there was no proof in his paper. And later, so in conference at Saint-Jacques, France, I asked Johann about this question. I say my doubt whether this is true. He told me that, okay, so this is true, he has a proof. Yeah, but I doubt at the beginning, but later I realized, yeah, he's reasonable. So actually, so we also have a proof, independent proof, and the proof is really inspired by the arguments in the paper of Carl Simpson. So how they show some fondness of the representation. So this is really in our situation here. And so Carl Simpson just proved that for a general connected component of the fiber, a connected component of F, so this is bounded. So this is bounded. So it's bounded, and also it's a normal subgroup. It's a bounded. So this is normal, and this is heuristic dense, unbounded. In G is almost a symbol. And from those data, we can conclude that the lemma shows that this is finite. This is finite. So using some Fraxes and building. But the idea, I think, is really inspired by the previous work by Collier and Carlos. And then, because it's finite, so we assume that the representation is B. Therefore, so F is a general fiber, component of fiber of A. So then this means that the dimension of F should be 0. And thus A should be generically defined onto the image. And similarly, we can also show that this is of log-drawn type, because we just look at the Taka fibration, because it's generally finite. So kappa x sp is also solely positive. Then you look at this logarithmic Itaka fibration. So you left F be a general fiber of J. So it's the fiber has 0 quadrilateral dimension. And moreover, so when you map it from F to A, so it's generically defined to the image. And we can prove that. So we need some effort. So it's also based on some previous result by Campana. We can prove that this is abelian. So it's not obvious because this is not proper. So this really brings some trouble. So it's not proper. If it's proper, it's direct consequence of the theorem Campana, but it's not proper. So we need some efforts to prove this. And okay, still the same reason. So it's a normal subgroup of rho pi 1x. Sorry, a rho should be the spectral covering pi star rho. I using rho to stand for pi star rho. And let's take the heuristic closure. So this is G, but this is some tori. So because this is almost a symbol, so this must be finite. And therefore, rho pi 1f is finite. So this shows that so the Itaka fibration is birational. So it implies that spectral covering is of log-drawn type. Now, the last 2 minutes, I want to explain how to spread the positivity. So now we have proved that the spectral covering is log-drawn type. The last step. So I want to prove that X is of log-drawn type. So this is really a difficult task. So it was previously in his paper, he using some really difficult result, which was later proved, and his announcement is not corrected. The corrected announcement was made by ACDU's paper, because he says that, okay, so for the leaves, the leaves induced by the harmonic mapping, so the dimension should be equal to the dimension of the partial algebraic morphism, the image of the partial algebraic morphism. So in other words, so roughly speaking, so the rank of the spectral forms should be equal to the dimension of X. So if rho is big, but actually I don't think we can prove this. So we have really to add some more representations. Like Philippe did, using some absolute constructible or just the whole space of representations to add several representations to achieve this. So, but it really relies on some deep result by Simpson's Leftier theorem, and its modified version by Philippe. So the more involved version by Philippe. So so when we try to prove this, I was really annoyed by this because it's really difficult to have such a theorem in the quasi-projective cases. But fortunately, I use extra 2 minutes to explain it. So we can avoid this just using some other ideas. So okay, so you look at the ramification. As I say, the ramification locus of pi is equal to this, just this one. Okay, and then I define as E to be the locus where it's unramified, it's ramified. So by the purity, E is a divisor. on X. And then I define a forms. So just using these to construct some forms. So G, so eta I is not equal to eta J. So those are spectral forms constructed by multi-valued one form, pullback. So and G belongs to the Galois group. Then we really constructed some symmetric forms here. And it's the pullback of symmetric forms, M omega X bar log D here. So as it vanishes on this set, or on this, sorry, it should be inclusion. So this, by the construction, this section is G invariant for any G on H. So it descends to a section sigma in downstairs. Moreover, it vanishes on the set here, high on this set here. So one can see that it vanishes on the ramification locus E. So in other words, we have a morphism from OXE to the symmetric differential here. So this is the first data. And the second data is that, so we know that Kx bar plus D plus E is big. Because, so this is because X bar minus D minus E. So D is the boundary divisor. So it's eta to X spectral, open set of spectral covering, but spectral covering is John type. So this is John type. So we have the bigness of this one. So now we apply a deep theorem by Campana and Poen. So a criterion to show that actually Kx plus D is log John type. And this is how to prove log John type. And through the pseudo Picard hyperbolic, so we're using the nonlinear theory. And we also show that, yeah, it's more involved because we only have the hyperbolicity of spectral covering. So we really have to spread the hyperbolicity of spectral covering to X. So it's also requires some effort. So I will explain. So I stop here.
I have a question. John, sorry. This is just a small question. When you said rigid kind of beginning, does that mean rigid just as a representation of the group, or does it mean rigid as a representation with fixed conjugacy classes?
Well, it's rigid, so I think it's isolated point in here.
Okay, so if it's non-rigid, it means you can allow the conjugacy classes to monitor.
Sorry, so I cannot hear you.
When you say non-rigid, you mean non-rigid. You mean that you can have a family of representations that, and with conjugacy classes that are also.
Yeah, well, I say non-rigid. Do you mean non-rigid? So if it's non-rigid, I mean the row here, the irreducible, geometrically irreducible containing row is positive dimensional.
Yeah, okay, but it's the marginalized space. You're not fixing the conjugacy classes of the monogram at infinity.
So I clear very badly.
Are you fixing the conjugacy classes of the monogram at infinity?
Yeah, I do not consider any information on that. Yeah, I do not fix any information on this. I just look at all such things. I do not. I know that in your paper is correct. So you did something restriction here, right? Yeah, I do not fix any data. The infinity might be not quasi-nilpotent and any like that. Yeah, I want to add one remark. I think you proved that if the monodromy in the SL2 case, sorry, I should mention that. So the theorem on harmonic mapping. So if X is quasi-projective, and so in the SL2 cases, so this was already done by Colin Simpson. So they have some harmonic mapping here to the trees. I think you prove that if the monodromy is quasi-important, the energy is finite, right? Is quasi-important at infinity, then the energy is finite. I think in the high dimensional it's also true. Yeah.